we designed, there are total 20 lectures, and this is the first lecture. So every day we will deliver the 2 lectures, and so that's today also there are 2 lectures. So the first lecture is the properties and propagation of the electromagnetic waves. So the title of the course is primer of easily understand the microwave remote sensing, and then specifically the interferometric SAR remote sensing. So for that purpose, I to basically put this particular lectures, properties and the propagation of the electromagnetic waves. So this is basically the foundation of this particular course. So if you see here, the electromagnetic spectra, so the wavelength is basically varying from the cosmic rays to gamma rays, X-rays, ultraviolet, visual, infrared, then thermal infrared, microwave, and the radio waves. Okay, so all the wavelengths are there, but all the wavelengths we cannot use for the remote sensing purpose, especially for the space-borne remote sensing, because if we choose the space as a platform for the remote sensing, so for that the energy, the movement of the electromagnetic signal is basically between the satellite and the earth, and then again signal is going back from the earth surface to the sensor. So in this particular journey, atmosphere is in the between. So the atmosphere basically is not allowing the movement of all kind of the radiations or all types of the wavelengths, or you can say the most of the signals either absorbed by the atmosphere or reflected back from the atmosphere. So only few signals like the visual portion, infrared, thermal infrared, and the microwave portion of the electromagnetic spectra are allowed to move basically across the atmosphere. So for that purpose, the remote sensing is basically divided into 4 parts, like visual remote sensing, infrared remote sensing, thermal remote sensing, and the microwave remote sensing. Means whatever the portion we are using for the remote sensing purpose, so based on that we are giving the name of the remote sensing, starting from the visual to the microwave. But the radio waves, X-rays, ultraviolets, gamma rays, all are basically either absorbed or reflected from the atmosphere, and hence they cannot be used for the remote sensing purpose. But whatever we are using between the visual portion and the microwave portion, all the wavelengths we cannot use for the remote sensing purpose, because most of them, or you can say a few wavelengths within this particular range, are again absorbed or the blocked by the atmosphere, and again those things we cannot use, or those wavelengths we cannot use for the remote sensing. So you can say some waves are attenuated in the atmosphere, some waves are absorbed, some waves are reflected or refracted from the atmosphere. So that is basically the main hurdle in the remote sensing process. So this particular course is intended for the microwave portion of the electromagnetic spectra. We are not worrying about the visual portion of the electromagnetic spectra, or infrared, or middle infrared, or the thermal infrared. We are only focusing or concerned with the microwave portion of the electromagnetic spectra in this course. So if you see in general the role of the electromagnetic radiation, so here you can see the major source of electromagnetic radiation is basically the sun. So radiation from the sun is going in all possible direction, but part of it moving towards the earth surface, and after interacting with the earth surface, part of it is reflecting towards the other so many sides, but sensor is there in the space. So you can say that part of that reflected energy is also moving towards the sensor. So whatever energy is reflected towards or reach to the sensor, so that energy is converted into remote sensing images. So if you see, if 100% energy is coming from the sun, so you can say hardly 40 or 45% energy is reaching to the earth surface. Then out of that, again some energy out of 45% is reflected towards the sensor side, and again absorbed by the atmosphere or reflected from the atmosphere. Then again hardly 10 to 15% energy is reaching to the sensor, and that energy only is useful for the remote sensing application. So that much energy is converted from the analog signals or analog radiations or analog signal of the electromagnetic spectra into the digital spectra by the sensor, and that digital numbers are stored in a particular fashion. So that fashion is nothing but the satellite imagery. Okay, so that is the process of remote sensing, or you can say the flow of energy from the natural source of energy and the sensor in between the earth. So when this energy is coming to the earth surface, so what happens? Part of it is basically absorbed by the earth surface also. So whatever energy is absorbed by the earth surface, according to the Kirchhoff's law, that absorbed energy is basically emitted later on. So whatever energy is emitting later on, so that is shown in this particular diagram. So that emitted energy can also move toward this sensor, so that again can be converted into the images. So these two things are basically the examples of the passive remote sensing. Passive in the sense, in this particular these types of the remote sensing processes, we are using the natural source of radiation. That's why the name is passive. Okay, and another type of the process is like if we have specialized sensors capable to send its own source of energy towards the earth's surface, and after that after interacting with the earth surface, it is coming back, or you can say back is scattered toward the sensor. So this is also one way of remote sensing. So this way of remote sensing is called the active remote sensing, because the source of energy in this process is the sensor itself. So you can say sensor itself is sending energy and sensor itself is the receiving energy. So the entire process of energy movement is basically because of the sensor. That's why the name is the active sensor is called the active sensor, and the process is called the active sensing, or we can say the active remote sensing. Because remote means if this kind of sensing we are doing from a distance, remote means distance. So there is a huge distance or large scale distance between the sensor and the object, then it is called the remote. Okay, so remote sensing, that's what we can say the active remote sensing. This is called the passive remote sensing. So here the distance is also coming into the picture. So first thing is basically the movement of the radiation or the energy which is flowing, or you can say the movement of the electromagnetic radiation or electromagnetic energy. And second one is coming basically the distance between the sensor and the object. That's what the name is remote. And this energy flow is basically coming from the natural source or from the sensor itself. So that is basically responsible for the active and passive things. And another thing is basically the platform which we are using. Suppose that according to the distance, so the distance is basically few meters, then we can say this is the in situ remote sensing. If the distance is, let us say, few kilometers or tens of the kilometers, or let us say the platform or the sensor we are putting into the aircraft or the balloons like that, then it is that we can give the name like the airborne remote sensing. And if you are putting the sensor into the space, so hundreds of the kilometers distance is there between the sensor and the earth surface, then that is basically called the space-borne remote sensing. So based on the distance itself, we can categorize the remote sensing, and based on the type of radiation, we can categorize the remote sensing like visual remote sensing, infrared remote sensing, thermal remote sensing, and the microwave remote sensing. Okay. So if you see in nutshell, so the electromagnetic radiation has the dual properties. One is called the wave nature, another one is called the particle nature. So from the wave nature, basically the energy is consisting or explained as a harmonic or the sinusoidal wave. So there is no particle. Basically the movement of the electromagnetic radiation is in the form of the wave. So because of this nature, so many processes we can explain, like the reflection, refraction, interference, diffraction, and the polarization. So all these processes are basically explained with the help of the wave nature of the electromagnetic spectra. So this particular course is concerned with the interference. So one process that is called interference. So interference is nothing but if two signals superimpose with each other. So so they basically combine together, and somewhere the intensity of the combined signal increased, or somewhere the decreased, or somewhere it is of the moderate scale. So that resultant, or you can say the combined intensity, we are going to study, and based on that so many things we can extract. So this particular course is based on the interference process. That's why the name in the course is Interferometric Remote Sensing. Okay. So the interference we will discuss in detail. And another nature of the EMR is the particle nature. So because of that, so many effects like photoelectric effect, Compton effects, so these are the effects which are basically can be explained with the help of the photons or the quanta, or you can say the particles of the electromagnetic radiations. But in itself, we can understand, if we study the particle nature, then we assume the electromagnetic radiation is just like, a beam of particles. But in case of the wave nature, so then in that case we understand, okay, the electromagnetic radiation behaves like a wave. This is not wave means this is a continuous, propagation of this energy, not in the in a discrete way, or you can say discrete means in the form of the bundles or the photons or the quantas. Okay, so that discrete movement of energy photons is not there. That is basically continuous movement of the radiation. That's what we are calling it the wave nature. Okay. So if we understand the electromagnetic properties, so it gives us the qualitative as well as the quantitative descriptions. So qualitative, we can basically understand how the microwaves are created qualitatively, and how they are measured, means some energy things we can measure, either their polarizations, their energy levels, and other things. We can measure the quality, and we can also understand how they interact with the other type of the media, whether it is atmosphere or different types of the features on the earth surface, or any kind of the special phenomena which is happening near the earth surface, like some fog is there, or some rain is there, or some clouds are there. So if such kind of the situations are there, then how the signals are basically qualitatively interact, because in that case we are not measuring how much different deviation or the effect is, but we understand, okay, qualitatively what is the nature of the electromagnetic spectra is changing. And quantitatively we can also understand, like the quantify the physical processes, especially the scattering. And scattering processes we can easily uh, quantify in the form of the some parameters, and those parameters are like the frequency, polarizations, direction, because all the waves are governed by the amplitude, frequency, polarizations, and the direction of propagations. So all these things basically gives us the indications for the measurement of the electromagnetic spectra quantitatively. So if you see some points related to the electromagnetic spectra, so here you can see, as the name is the electro and the magnetic. It means some electric vector is there, as well as some magnetic vectors are also there. So, and both of them are basically propagating along the direction of propagation, and both of them are perpendicular to each other. So here you can say, suppose this is direction of electromagnetic spectra. So here you can say this wave is propagating like this. So somewhere it is going up, somewhere it is going down. So you can say the strength of the signal is, here it is 0, then continuously it is increasing, and it is becoming maximum, then again it is decreasing, and then going minimum, then again it is decreasing, becoming 0. So this is basically called the one cycle, because it is going up and then down, then becoming 0. It started from 0, going up, maximum, and then minimum, and then 0. So this is called the basically one cycle. And the distance traveled by the signal for this particular cycle, let us say from this 0 to this 0, is called the wavelength. And generally it is represented by the lambda. So the inverse of the wavelength is called the frequency. Frequency definition is just like how many cycles it is completing in 1 second. So suppose 100 cycle it is completing, so the frequency is the 100 hertz. If 1000s are there, then 1000 hertz. So in the remote sensing, though this electromagnetic spectra is having electric as well as the magnetic fields, but in the remote sensing process, we will only consider the electric field vector, because the magnetic field vector is not changing very rapidly, especially in the remote sensing process. Okay, so only the electric field vector is responsible for these types of the propagation plus the changes which are happening. So whatever the changes are happening on the surface, those we are basically understanding or analyzing with the help of or change of the electromagnetic spectra, or you can say electric field vector. So that kind of the things we will understand. And suppose this here you can see, though the electromagnetic spectra is consisting of both electric and the magnetic field, but if the frequency is very less, for example, for the extremely low frequencies, the electric field and the magnetic fields are specified separately, means both we can describe separately, but at the higher frequencies, electric and magnetic fields are not separable. So very high frequencies means below the visible portion, or let us say ultraviolet, X-rays, gamma rays, there the frequencies are very high. It means the electric and magnetic fields cannot be separate very easily. But for the longer wavelength, let us say radio waves or microwaves, there the wavelength is very high, but the frequency is low. So there we can separate both the electric and the magnetic fields easily, and wherever we want to use them separately, we can use. So electric field vector can be separated and can be used for the remote sensing purpose very easily if we are using or working in the microwave electromagnetic spectra. So here basically this is the mathematical descriptor of the electromagnetic field or electromagnetic radiation. So here you can say this is the three-dimensional representation. Let us say this side y-axis is the magnetic vector and the x-axis is the electric vector. Both are perpendicular to each other, and this z direction is basically representing the direction of propagation. It means all three are perpendicular to each other. And if we just concentrating on the electric field vector, so the electric field vector we can describe like this: E equal to E0 e to the power j phi. So here are basically two parameters, phi and the E naught or E0. So E0 is basically called the amplitude of the signal and phi is called the phase of the signal. So you can say this signal is made up of the amplitude and the phase information. So if we extend it the phase information, so phase information means phi we can replace like omega t minus k dot r. So omega t is a phase, that is called the temporal phase. K dot r is again another type of the phase called the propagation phase, or you can say the geometrical phase of the signal. So you can say the phase is replaced by linear combination of the another phases. So this is temporal phase, this is the geometrical phase, and this is the amplitude. So each electric field vector can be represented in terms of phase and the amplitude. If we apply here the Euler's theorem, then this expression can be written as E0 cos phi plus j times E0 sin phi. It means the first part E0 cos phi becomes the real part of the signal plus j times E0 cos phi becomes the imaginary part. So you can say this electric field vector is having real part plus the imaginary part. So you can say the electric field vector is complex in nature. So you can say this is the complex signal. So whenever we talk in the microwave remote sensing, or there basically we will study the complex signals, not the simple signals, or you can say the real signals or the imaginary signals only. We will study the complex signals, or where we will have the real signals as well as the imaginary signals, or in other words we can say where we have the amplitude information as well as the phase information. So amplitude, sometimes we call it, okay, let us have the amplitude images of the satellite or the phase images. It means in that case we are talking about E naught and the phi. If we have the phase images, it means we have the phi information, and if we have the amplitude images, then we have E naught. So from the amplitude images, we can describe the intensity images also. Intensity is directly proportional to the square of the amplitude. So somewhere in the remote sensing, somewhere these amplitude images are very useful. Somewhere this phase information is very useful. Somewhere both of them are very useful. This is basically depending upon what kind of the problem we are going to handle. So for example, one branch is called the polarimetric SAR remote sensing. So in polarimetric SAR, basic polarimetric SAR remote sensing, we are using only the amplitude images, which are useful for the characterizing different types of the features or different types of the scattering mechanism which are happening in the resolution cell itself. Okay. And if you are talking about somewhere, in the advanced kind of the polarimetric SAR remote sensing, so somewhere just to improve the accuracy level, we are basically involving the phase images also, just for the enhancement of the accuracy level. Okay. So, but in general, in polarimetry, the amplitude information is basically analyzed. But in a case of the interferometry, we are concerned with the phase images, because if we suppose we are comparing two signals, so we can compare the phases of two signals. So we are subtracting, let us say, a phase of first signal minus phase of second signal, so that we can represent like, let us say, delta phi. So that is called the interferometric phase. So the phase difference of two signals is representing the interferometric phase. So that phi 1 minus phi 2 is very much related to this particular course. Or you can say in the interferometry, we are only concerned with the phase images. But the phase images, the beauty is basically these images are very, very sensitive. You might be aware about the relationship between the phase difference and the path difference. Like phase difference equal to 2 pi upon lambda into path difference. Okay. So from this expression itself, you can understand phase difference equal to 2 pi, which is a constant, upon lambda. Lambda is the wavelength of the radiation which we are using. Let us say that is the microwave portion. Generally, it is from between the 1 millimeter to 1 meter. Any value it may have. So lambda is also known. Then the path difference means the movement of the target on the earth surface from initial position to the final position. Suppose some target was there at position, let us say P1, and after some time the target has moved from P1 to P2. So from P1 to P2, that is called the path difference. And phase difference is basically phase difference of two signals. Means first signal, let us say, was acquired before movement of the target, and second signal was acquired after the movement of the target. So this phi 1 minus phi 2 you can calculate. It means pre event and the post event phase you have. So post event minus pre event is called the phi 1 minus phi 2, or you can say delta phi, or you can say interferometric phase. So this phase difference equal to 2 pi upon lambda into path difference. So phase difference you can calculate from the phase images, and path difference you can calculate from this relationship. So point is, if you know the phase difference between the two signals acquired pre-event and the post-event, then you can calculate how much the target has moved from pre-event to post-event. So that movement you can calculate, and how much movement means what kind of scale you are expecting. Means if that movement is very large or very low, small, means which scale of the movement we are talking about. So that scale is very, very small, very, very small, in the sense, suppose some target is moving only few centimeter in 1 year, or few millimeter in 1 year. So that movement is very, very slow. If this type of this slow movement is there, so this movement we cannot observe from our eyes. Suppose we are sitting somewhere on the earth surface for 1 year, and something is happening, or you can say some kind of motion is happening on the earth surface, and that, let us say, 1 centimeter or 2 centimeter movement was happened in 1 year, so that we cannot see from our eyes. But these microwave remote sensing images can see in 1 year how much motion was happened, or let us say 1 centimeter or 2 centimeter happened, so they can catch very easily. So you can say a millimeter scale movement can be depicted with the help of these phase images. So that's what I'm saying. These phase images are very sensitive with respect to the motion. So you can say the interferometry is applied whenever we are interested in the motion of the target, or we want to analyze the motion of the targets on the surface. Okay, so there are various examples of this very slow motion. I'm talking about few millimeter or centimeter per year. This is not like the movement of your aircraft or movement of your car. That is very fast. Those types of the motion you cannot analyze with the help of the SAR images, because those are very fast movement. Here we are talking about very slow type of the motion. Okay, but yes, there are examples of the slow motions also. For let us say, if you talk about the plate tectonic movement, so those plates are moving very slow. Let us say in 10 years or 1 year, 1 centimeter, 2 centimeter plates are moving. Let us say our Indian plate is moving towards the Asian plate, so that motion is also very slow. We are not able to see from our eyes, but those things you can see from the microwave remote sensing images. Okay, so that this type of the motion is very slow. Same examples may be like glacier melting. So glaciers are melting, let us say, in one season. Okay, in some summer season, 1 year only one summer season is there. So in 1 year, let us say some melting happened 2 centimeter, 3 centimeter from the top glaciers. So how much the motion is happening? Motion means initially the glacier was somewhere up to some height, and after melting it is guessing basically the top elevation is getting reduced. So that is again few centimeters. So this is also called a kind of motion, because this motion is happening in the vertical direction. So wherever this path difference I'm talking about, it means this is the movement of the targets on the surface, but that movement may be in the horizontal direction, or maybe in the vertical direction, or maybe in any kind of the inclined direction. Okay, so that way we can say this motion may be in three-dimensional way: one-dimensional motion, two-dimensional, three-dimensional, or now we can talk about the four-dimensional also, because time is also considered. So time can be considered as a fourth dimension. So here we basically I have mentioned this x, y, z, and t. It means x, y, z is representing the positional coordinates, t is the temporal coordinates. So that's what I'm saying. This phase is basically varying with respect to four dimensions. Okay, so from this phase information we can depict very slow type of the motion. Another examples may be like your land subsidence or the landslides. Landslide is also very slow process. Or some buildings are tilting. So that buildings are tilting, it means that is also a kind of motion, and that motion is again very slow, few millimeters in a year or 2 year. Same way, some dams are there. So dams are also getting tilted over a period of time, or some historical buildings. So those are also tilting. Bridges, those are also getting affected. So whatever the changes are happening, those are very slow in nature. So all kind of such processes you can analyze with the help of these 5 images. So 5 images, or you can say the phase image, is very important. Now another branch is being developed, that is called the polarimetric interferometric SAR. Means we are combining both polarimetry as well as interferometry. That is called Pol in SAR. So where we are basically using amplitude images as well as the phase images. So those are basically some advanced kind of analysis. So this is another representation, just like a sinusoidal wave. So here you see this is the phase. Here it is 0. So phase is 0. As this distance is increasing, phase is increasing. So here it is basically a pi by 2. And then again the phase is increasing. Here becomes pi. And then this is 3 pi by 2. And here phase becomes 2 pi. So you can say in one complete cycle, phase is changing by 2 pi. And this gap from here to here, highest gap is called the amplitude. And the distance from here to here, it is called the wavelength. And this complete cycle is called the hertz, 1 hertz, or you can say measure of the frequency. So now another way of representing a only real part of this signal is phi equal to a times sine omega t plus phi. So omega t means 2 pi f t plus phi 0, or phi maybe scattering phase or the geometric phase, something like that. So again we are basically concerned with the amplitude and the phase information. So now here we can see the type of the motions or the vibrations or oscillations which are happening in the waves. So here you can see this is the example of the longitudinal wave. Suppose some spring is there, we are fixing at the wall and we are pushing away from the wall or towards the wall. Suppose we are pushing elongating away or putting away or putting force away from the wall. So somewhere what happens, this is elongated, somewhere contracted. So this is basically kind of the motion, but this motion is happening along the direction of force wherever we are applying, either towards the wall or away from the wall. So somewhere elongation, somewhere contraction is happening, but the vibrations which are happening in this spring, those are along the direction of the applied force. But here if you see, this is the example of the translation wave. Suppose one rope is there and if we are putting up and down, so these types of the wave is generating. So vibrations are basically perpendicular, or you can say the transverse along the perpendicular to the wave. So these types of the waves are called the transverse waves, and the electromagnetic wave is the example of the transverse wave. So this electric field vector, and again here you can see the electric field vector. We are concerned about the electric field vector, not the magnetic field vector. But electric field vector is again a three-dimensional vector. Means it can have x component, y component, and the z component. So z component generally we consider as 0 because that z component is along the direction of propagation. So only two components are deciding the movement of the entire electric field vector. So what we can do, we can basically stop the vibration along any of the direction wherever we want. So suppose, and we, or in other words we can say, we can allow the vibration of the electromagnetic field uh, whatever we want. So suppose we are allowing the vibration along the horizontal direction, then this electric field vector is called the polarized electric field vector. So you can say the vibrations are happening only in a particular direction. It means that the wave is polarized. If that vibration is in the horizontal direction, then you can say it is horizontally polarized. If those vibrations are along the vertical direction, then it is called the vertically polarized. If you are allowing the horizontal as well as vertical, then what happens? The resultant of horizontal and vertical will be somewhere else, and that resultant will change according to the strength of the signal. Suppose here it is maximum, here it is maximum, so resultant will be maximum. Here the strength is less, here the strength is less, so the resultant will be less. So that the resultant of horizontal and vertical electric field vector will change everywhere, or you can say according to the position as well as the time also. Okay, so if this is changing, and if you are looking from the front side or the back side, then you will realize the resultant vector is basically moving in the form of the sphere. So you can say the trace of that or no arrow of that resultant vector is like a ellipse. So you can say in that way, you can say that is the electrically polarized, or sorry, elliptically polarized signal. So and in so you can say if both horizontal and vertical are there, then they are forming the elliptical polarization. If the amplitude of both the waves is same everywhere, then we can say that elliptical ellipse can be converted into circle. So in that case, we can say that is the circularly polarized wave. So now you just keep in mind there are three types of the polarization. One is called the elliptical polarization, another one is the circular polarization. And another one is called the plane polarization. Plane polarization may be either horizontal polarization or the vertical polarizations. So the horizontal or vertical polarization is also called the linear polarization, but normally we call them as a plane polarization. Okay. And in all remote sensing, especially the microwave remote sensing, we are using plane polarizations only. Very rarely we are using circular or the elliptical polarization. I don't think is there any sensor is using the elliptical polarization, but circular is being used by the RI set Indians, RI set 1 or RI set 1A. In both we are basically using the circular as well as the plane polarization, but no one else is using circular or the elliptical polarization. Okay, so only Indian sensor is there which is using the circular as well as the plane polarization, so that both of them combining together, so that's what the sensor is also called the hybrid polarized sensor, or we can say that is compact polarimetry sensing we are applying. So these are some examples of the elliptical polarization ellipse like this. Just as I mentioned, if you analyze the resultant of the horizontal and the vertical component of the electric field vector, so the that basically will move just like a ellipse. So this is called the ellipse, or you can say this is the trace of that resultant electric field vector. So that's the geometry is coming like a ellipse. That's what it is called the polarization ellipse, governed by three parameters. This is phi, and this is tau, and this is a amplitude. Amplitude is called ellipse amplitude, described in terms of the x and the bi component, or x and bi amplitude, or x and bi component of the electric field vector. And this is called the orientation angle, or angle of ellipse, phi. So phi is described with the help of this particular equation, and the ellipticity angle tau is basically described with this particular type of the expression. So point is, if you have the elliptical parameters of polarization ellipse parameters a, phi and tau, then you can also describe the entire propagation of the electromagnetic field. This is another example of the polarization, or you can say you can decide the type of the polarization based on the phi and tau values. So here you can say this is elliptical polarization, circular polarization, this is pi polarization. So you see here the orientation angle phi, that is 0, and the ellipticity angle is 0. Both are 0. It means this is the example of the horizontal plane polarization. That you can also understand from this particular graph. For example, this phi is 0. It means this particular line will lie on the x-axis. Okay, so this types of the width will go out, and tau is 0. It means the distance from here to here will be 0, or you can say this line will lie on the this line. So, and this line is lying over the x-axis. So you can say everything is lying on the x-axis. So x-axis is basically horizontal polarization. So that way, just you can imagine the values of phi and tau, and accordingly you can understand, okay, if phi is 90 degree, tau is 0, then it is vertical polarization. If theta phi is any angle, like not 0, that may be 10 degree, 20 degree, 30 degree, something like that, but ellipticity angle is 0, then it is called the linear, or you can say inclined polarization, or linear polarization at angle theta. And left circular polarization, if phi is varying minus 90 degree to plus 90 degree, and tau is 45 degree, then it is called the left circular polarization. And if it is minus 45 degree and phi is minus 90 degree to plus 90 degree, then it is called the right circular polarization. Apart from this, it is called the circular elliptical polarization. Another example of these linearly polarized signals, here you can see the red signal and the green signals both are moving like this. It means this is the horizontal polarization, and this is called the horizontal polarization. This is vertical polarization. This is inclined, or you can say linear polarization at minus 45 degree. This is linear polarization as plus 45 degree. This is the example of the elliptical polarization. So here you can see as I mentioned, this is, let us say, x component of electric field vector, and the green one is, let us say, green one is x component, blue one is a y component. So the resultant will basically move something like this, just like, helix. So this is basically, this is forming a ellipse. If you just connect like this, it means this is forming a ellipse, and that ellipse is called the polarization ellipse. So here you can say, if it is the direction of this ellipse is clockwise, then it is called the left circular, and if it is anti-clockwise, then it is called the right circular. So according to the motion of this ellipse, you can decide whether it is right elliptic ellipse or the left ellipse. Just compare, like, clockwise or the anti-clockwise. Here, this is the formation, means how we are basically generating the polarized signals. So from this figure, you can just see, suppose this linear polarization we are putting. So linear polarization means one polarizer is there, or you can just simply a slit is there, and one sharp line we are creating. So if ordinary signal is coming, okay, so that will come from this single line itself. So you can say, from outside this polarizer, only these lines we are observing. So you can say these are basically only linear signals we are observing. Here you can say this is the ordinary light or unpolarized light. So vibrations are happening in all possible direction. Once it is crossing only this horizontal line, or you can say single line, or you can say simple plane, then whatever is going out, means whatever radiation is going out, that will vibrate only in a single direction. So that is called the linearly polarized light. So now it is in our hand. This line we can draw horizontal, or we can draw perpendicular, vertical, or we can draw at particular angle also. This is up to us. Means if it is this line is in the horizontal direction, then these vibrations will happen in horizontal direction, and that light is called horizontally linear polarized light. Okay, or you can say horizontal polarization. If this line we are putting, in a vertical plane like this, then we are getting vertically polarized light. If we are creating like this, it means this is the linearly but at angle theta. So that may be plus 45, minus 45, plus 60, minus 60, minus 48, something like that. So any angle which is we are using, but in all these cases, whatever the output is there, that is linearly polarized only. So you can say if theta is 0, then it is horizontal, theta is 90, then it is vertical. If it is in between, then it is linear at that particular angle. Now if you see, if this types of the line means vertical, as well as here we are basically putting another polarizer, but this is called the quarter wave plate. Quarter wave plate means we are putting, vertical line as well as the horizontal line. It means from the vertical line as well as from the horizontal line, both the signals will go out. When they will go out, then they will form the resultant, and the resultant will move either in the clockwise direction or the anti-clockwise direction. So you can see these are the resultants. So the resultant is forming, and those are changing. So you can say this is moving something like this. So suppose you are you are standing this side, so then you will feel basically this is clockwise movement is happening. Clockwise means that is left elliptical polarization. And if that movement is like this way, then you will feel that is anti-clockwise. Then you can say that is right elliptical polarized light or radiation. So according to these polarizers and the quarter wave plates, we can generate a polarized signals whatever we want. Now this is the combination of waves, like when we are able to combine two signals, then only we can apply the interferometry. So here you can see this is the one signal. This is sinusoidal signal. This is another signal which is again a sinusoidal signal. And if we superimpose them, means combine both of them, and the phase difference between these two signals is 0, means both the signals are behaving in the same manner. So when we combine them, so the resultant will be increasing. Means wherever the maxima of maxima will be there, minima of minima will be there. So overall amplitude of the signal will be enhanced. So this is basically called the interference, but this is called the constructive interference because the strength of both the signals is utilized in a positive manner. So the overall intensity or overall strength of the final or resultant signal is increased maximally. So it is called the constructive interference. And suppose this is the situation, first signal, second signal, but both of them are just opposite to each other. Opposite to each other means the phase difference both between both the signal is pi, or you can say the 180 degree. 180 degree means if this signal is having the maxima, another signal is having minima, just opposite of the each other. So if we combine both of them, then what we will get? This is maxima, this is minima, so we will get 0. Here this is maxima, this is minima, so again we are getting 0. So everywhere of this signal we are getting 0. So what we will get? This simple line we will get, or you can say 0 strength signal we are getting. So this is called the destructive interference. Interference is there because we are combining two signals. If you are not combined, it means that is not interference, but when we are combining them, it means it is happening interference. And if suppose the same signals are there, but the phase difference between both of them is pi by 2, or you can say 90 degree. So another signal is, or you can say resultant signals will have the moderate strength. Means that strength is more than this, but less than this. So you can say there may be another positions also. Means the phase difference between these two signals may be 80 degree, 90 degree, 92 degree, 95 degree, 130 degree, 160 degree, something like that. So you can say whatever the phase difference between the signal is, that will decide what will be the strength of the final signal. So that way we can say there are number of types of the interference between constructive and destructive interference, but generally we understand or we know the constructive interference and destructive interference. But keep in mind, between constructive and destructive interference there are number of interferences where the intensity varies between 0 and the maximum, which is in the constructive interference. So this way you can also understand. For example, this is the first signal, this blue one is smaller one, first signal, and this another one is the let us say second signal. So the phase difference is equal to phi 1 equal to phi 2. It means phi 1 minus phi 2 is 0. So if it is 0, it means the strength of combined strength or resultant strength will be high. So the red color is showing the combined strength, which is maximum. Here you can see the first signal is this side, another signal is this side. So phi 1 phase of this one is phi, this one is this is phase of this one is 90, phase of this one is 270. So 270 minus 90 is pi. So pi phase difference between these two signals is pi. So you can see one is working towards this side, another working towards this side. The resultant will be 0. So that resultant is shown by red dot, means no strength of the signal is there. If here you can see this is the first signal, this is another signal, but phase difference between them is pi by 2. So this is one vector, this is another vector. So from this tail to this arrow, we can draw a vector. So that is called the resultant vector. So that way we can understand, okay, these are the strength of the resultant signals. So those strength will work, and this is basically called the interference or coherence. Coherence means the similarity between the signal. If coherence means similarity between the signal is very high, so they can basically form the constructive interference. If the similarity is very less, they will form the destructive interference. So these are the formula for coherence. Coherence is just like coefficient of correlation. So that way we can calculate these things. Now time is very less. I'm quickly finishing these two, three slides. That is called the propagation through media other than vacuum. So these three parameters are very important. One is called the electric permittivity, epsilon, magnetic permeability, mu, and the electric conductivity, which is G. So as you just recall the Maxwell equations, So these quantities are basically used in the Maxwell equations. So this permittivity and permeability are very important. But permeability is used for along with the magnetic fields, but permittivity is used for the electric field. So here we are analyzing electric field vector. So we will basically only understand the behavior of the permittivity. So permittivity is basically related with the um, dielectric properties of the media. So if dielectricity is very high, it means those medium will behave different. If dielectric constant is less, so those behavior will behave differently. Okay. So these are the Maxwell equations. I'm not going to describe this. So everybody understand the four equations are there. So both are available in the differential as well as the integral forms. So these things we can skip because for free space, some assumptions are there like sigma is 0, mu epsilon is epsilon 0, mu is mu 0. So that way, and this electric permittivity is complex in nature, or just like here, the relative permittivity we are expressing as a complex number, which is real, having real part and the imaginary part. And relative dielectric constant can be defined by dielectric constant of the media versus free space. So this ratio is called the relative dielectric constant or relative permittivity, which is complex in nature. But in remote sensing process, this real part is very important because this is related to the reflection, and this second one is related to the absorption. So in generally remote sensing processes, we are ignoring the absorption part, or you can say the second part is somehow indicating the loss of the signals. So yeah, so this velocity of the signal through a particular media is related to the velocity of light and square root of the relative dielectric constant. And this is skin depth, or you can say the penetration capability of the signals. So microwave signals having the longer wavelength. So the penetration capability of the microwave signals is more compared to the other signals of the other microwave signals. So here you can say the skin depth or the penetration depth is proportional to the wavelength, means more wavelength, more skin depth, and also related to the directly proportional to the square root of the real part of the relative dielectric constant. It means more dielectric constant, more skin depth. But this second part is real part of the dielectric constant. If it is more, it means the penetration capability will be less. So if media is absorbing more signals, then it can penetrate less. The meaning is that. So in microwave remote sensing, everywhere we will talk about the penetration capabilities, because in remote sensing we have to deal with different types of the medias like forest covers, agriculture fields, or the barren land, or bare soil, or open soil, rocks, glaciers, everything we have to analyze. So basically we have to understand dielectric constant of different types of the behavior or targets, and accordingly we will basically choose which type of the microwave signal is useful for which types of the domain or applications. This is the soil moisture is another important study where the soil basically, if you see in the soil, some soil particles are there, in between some air molecules, air space is there, and some water content is also there. So the water content is increasing. It means the dielectric properties of the soil is increasing. Or you can say that epsilon is increasing. So from the microwave signals, you can extract those epsilons very easily, and you can understand, or you can investigate the soil moisture content over the target. So the soil moisture estimation can be done using the microwave signals very easily. So these are the graph between the soil moisture and the real and imaginary parts of the dielectric constant. So you can see the imaginary part is having less role, but the real part of the dielectric constant is varying almostly, linearly with the soil moisture. So this, yeah, this is basically the absorption reflection just like if some incident radiation is there, but the transmission is not happening in case of the remote sensing, because the signal is coming on the earth surface, so it cannot transmit from one surface to the other side of the earth, so transmission of the signal is not possible. So these things you can just see, because this is just related to the incoming radiation to the outgoing radiation, and these are the type of the scatterings. So three types of these scatterings are there: Rayleigh scattering, May scattering, and the uh, non-selective scattering. So this is the relationship. If the wavelength of the radiation is much greater than the size of the particles or diameter of the particles, then whatever the scattering is happening, that is called the Rayleigh scattering. If the wavelength and the diameter of the particle is almost same, then it is called the May scattering. And if it is independent of the wavelength and the size, then it is called the non-selective scattering. So thank you so much. So this is, we come to the end of the first lecture. So if you have any questions, we can discuss.